Okay, sorry. Applications of calculus. Whew, okay. Now, guys, for all of these applications, we are going to keep referring back to the graphs, all right? Because we know that calculus is actually the study of change, but we always bring that back to gradient, all right? We remember that the derivative of a function is always the gradient of that function. So let's just write that down. I'm going to write f dash x. I'm sure we're all fine with that being the derivative. That is the gradient. But guys, if we're thinking of a graph and how a graph changes, the gradient is also actually the rate of change of that graph. I hope that makes sense, because remember the gradient is the slope. So if we're thinking of a parabola, for example, all right, as it goes up, it is changing, all right? The gradient is the rate of change. There, the gradient is 0, and there, the gradient is now negative, all right? But at every point, the gradient is actually changing as well, right? Because it's the gradient of the tangent there. So the gradient is actually also the rate of change of the graph. So we're going to use that, and we're just going to say that whenever they're asking you for the rate of change of any type of function, because now it's also again going to be real world application type questions, you'll see now when you do it, we're going to just remember that the rate of change is actually the derivative, all right? And it's basically, that's what we're going to do. You'll see now when we do the examples, the types of questions that they ask you. So let's just write here, rate of change at a specific value is equal to f dash x, the derivative, at that value. Okay, that might still sound a bit fuzzy, but you'll see now when we do the examples. So I think let's just jump straight into those so that you can see how they ask these questions. Okay, the surface area of a spherical balloon is given by, yo, sorry about that. So they do actually give you the formulas as well in these types of questions, which is quite nice. I'm not sure if you guys know that the surface area of a sphere is 4 pi r squared. Okay, I actually can't remember. Did you guys do these types of questions?
I think in
grade 9, in grade 9 maybe. In grade 8 you did just like the normal, do you remember that packaging thing where you had to build those boxes? Okay, but then in grade 9 I think you would have done spheres, cones, and pyramids. Anyway, they do give you the formulas. Okay, I'm just going to write the whole thing. I'm sure we all know that r is the radius of the balloon, but let's just write it in, where r is the radius of the balloon. Okay, guys, I want us to highlight rate and then changing. They haven't actually used the specific words rate of change, but they are implying that, I think, all right? Saying calculate the rate at which the area of a balloon which is being inflated is changing. So guys, they're asking for the rate of change of the area when the radius is 5 centimeters. All right, so those are the important bits of information there. They're asking for the rate of change of the area because they're saying the rate at which the area is changing. And then when the radius is 5 centimeters, that is the value that we're going to have to sub in. All right, so rate of change of a specific value is the derivative of what? What do we think in this case? So they're asking for the rate of change of the area. So it's going to be the derivative of the area at that value, at the R value of 5. Yeah.
So I understand.
Mhm.
Like how you could even do this question if you don't know like, how fast someone's going up the balloon. How is it always changing at the same rate?
It isn't always changing at the same rate. That is why we're going to sub in a specific value. Guys, if we're thinking of a balloon, hey, it starts off with a very small, I mean, when it's that flat thing, I don't really think you can really say that it has a surface area. Then when you start blowing it up, at the beginning, it gets quite big, quite quickly, right? So the surface area is changing rapidly at the beginning. Then as you keep blowing and blowing and blowing, when it's like quite big, it doesn't get that much bigger all the time. Does that make sense?
Yeah, I was thinking about it in terms of time, but it's not.
Yeah, but they're not saying in terms of time. Do you see they're saying in terms of the radius? Yeah.
So you're not calculating the speed at which the balloon gets bigger, you calculate the area of the balloon relative to the radius.
You're calculating the rate at which the area is changing relative to the radius. Yes.
Not
Yeah.
compared to like,
Yeah, not compared to time. Because guys, also if we're looking at this formula, there is no time in this formula there. It just has to do with the radius. Yes. Yeah, it is a bit confusing, guys, and you'll see it, especially when we have to get the what's it called? The unit of the answer. That's actually the difficult part of these types of questions, is writing the correct unit. Okay, but guys, are we fine with rate of change being the derivative? Okay, so let's just write that. Rate of change. And now, guys, we can't use f dash x. Let's practice using the correct notation. All right, what are we going to find the derivative of? The derivative of the area. So let's say dA over, and what is the variable in this formula? R. So the derivative of the area in terms of the radius. And then I'm just going to write here at R equals 5. Okay, that's what we're going to have to sub in. Okay, guys, what is the derivative of this area? Remember that pi is a part of the actual number, so 4 pi r squared. So it's going to be 8 pi r. 8 pi r. But then they've told us that at the specific radius that they want us to write the rate of change or calculate the rate of change at, it is 5. So we're going to sub that in. So 8 pi times 5. And guys, you do actually, I know it's a bit of a pain, but you do have to show that you're subbing it in. All right, they give a mark specifically for subbing that value in. Then you can actually just leave this in pi form. What is that a thing? Is that a word? 40 pi, that's fine. Or you can write it in decimal form, it's okay. Now guys, the unit here, you're actually going to use this to set out your unit. So the way that I always remember it, because rate of change, the area is changing. Now, what is the unit of the area? If the radius is centimeters, then the unit of the area is going to have to be centimeters squared. All right, so the area is changing, centimeters squared, but how is the area changing? The area is changing relative to the radius. Now, what is the unit of the radius? Centimeters. So you have to write per centimeters. So at the point where the radius is 5 centimeters, the area of the radius, or not of the radius, sorry, the area of the balloon is changing at 40 pi centimeters squared per centimeter, right? But then if it was 6 centimeters, for example, it would be a different value, but you would still have the same unit. So guys, I always look at this thing, hey? It's the unit of the area first, the unit of the one at the top, per the unit of the one at the bottom, if that helps, right? The unit of the actual quantity that we are calculating the rate of change of per the unit of the thing that we're subbing in. Yes. They can ask these types of questions in AP. Yeah, we are going to do a few when we're done with this, but yeah. So guys, it is quite useful to use this notation. I don't think it's that difficult really, if we just practice it. Yeah. No, not really. Yes, so at that specific point, it's almost like when we're finding the equation of the tangent, at that, only at that specific point is that the equation of the tangent. So yeah, it's a bit of a silly thing. We're going to do another example now where we're asking different types of questions as well, not just rate of change. So maybe, yeah, but guys, that's basically it. All right, if they're asking for the rate of change, you find the derivative and you sub in the value that they're giving you. Okay, it's just this that might be difficult, and they actually give a separate mark for having the correct unit as well. So they will give a mark for 40 pi and then a mark for the unit. All right, so the answer will be 2 marks. So it's quite important that we're getting that unit correct. Again, first the unit of the one at the top, and then per the unit of the one at the bottom. Okay, number 2. Okay, guys, 2.1, calculate the rate at which the volume is changing. Are they telling us at what specific time? Just the general rate. All right, so we're just going to find the derivative, and that is the answer to this one. So we're finding the derivative of V in terms of T, right? The derivative of the volume and the variable that we have there, time, is T. So what is the derivative of 2,500? 0. The derivative of 500t is 500. And then we are finding the derivative of this one. Now, guys, what is 1 over 8 times 2? 1 over 4. And then t. Okay, now if it's just a general one, you don't have to write a unit. You can if you want, but we are going to do the unit for the next one. Because in 2.2, they're now going to give us a specific time. So now they're saying, calculate the rate at which the volume is increasing. And guys, whether they say increasing or decreasing doesn't really matter, all right, because it's still changing, all right? If something is increasing or decreasing, still changing, they're just being specific by saying increasing, but it won't actually change our working. And then when T is equal to 500 hours. Right, so easy, we're going to take this. This is basically now the formula for the rate of change, right? And we're just going to sub in 500 hours for T. So I'm going to say dV over dt. And guys, also they can be tricky, hey? They can, because remember that T is time in hours. So what if they said 500 minutes? You would have to convert it. All right, that's just something to be on the lookout for. You do actually need to pay attention to what unit they've given you your stuff in. Okay, so 500 minus a quarter times T, which is also 500 in this case. And then we will get 375. Now we do have to write our unit. Now guys, what was the unit of the volume here? Thousands of cubic meters. All right. Now you can write it out, thousands of cubic meters, or you can also just say 1,000. Or you can actually do the 000 if you wanted to, but I just want to show you that this would also be fine. All right, so 1,000 meters cubed, you can do it right like that. So that was the unit of the value at the top of the volume. And what is the unit of the value at the bottom? Hours. All right, so you're going to say 375,000 meters cubed per hour. Yes. Yeah, should be fine. Okay. 2.3.
No, we have to like set up formulas that to do with the thing.
Possibly. I haven't really seen it being asked that way, but yeah, they could. Okay, now guys, calculate when the volume of water starts to decrease. I mean, what are they even asking here? Let's look at the function that they've given us. What type of graph would this function be if we had to draw this? A parabola, but do we see that our A value is negative? All right, so it would be a negative parabola, so it would be a sad face. It would be this kind of situation. All right. Now guys, if this is representing the volume of water, all right, here it's increasing. What happens here? That's the turning point. And do we remember that the rate of change, remember, is the derivative? So at the turning point, the derivative would be 0, all right? Now what happens just after the turning point? It starts to decrease. So guys, what you need to, I don't know, it seems like a bit of a stretch, all right? But this is like I suppose a dam of water, as soon as it gets full, as soon as it gets to its maximum volume there, it will start running out, I suppose. Is that how it works? Yes, okay, because it can't keep going fuller and fuller, all right, if it has a certain capacity. So at 0, there at the turning point, that would be the maximum value, all right, the maximum volume in this case. And then after 0, it would start to decrease, all right. Okay. Well, isn't it that there is like a, how does it work if it's like a water catchment dam? Yeah. It would decrease from that amount, because doesn't it start running out? Would it? I'm not sure. I mean, we can Google it. I mean, this is what we need to assume in this case. All right. Yeah, but I see what you are saying. But yeah, okay. Are we fine with that being the maximum? That's when the volume is at a maximum, and then it's going to start decreasing. But guys, it does come from the fact that this is represented by a parabola. Okay, I'm not sure if all water dams will have a volume that could be represented by this kind of formula. Okay, but it depends on the formula that they're giving us. So let me just write a little note here. I'm running out of space a bit, but let's just say at that point, dam has reached its max volume, and that is at the turning point. So basically, guys, what they're wanting us to do is to find where the turning point of that function would be, at what t value. Now, how do we find the turning point? We're going to make the derivative equal to 0. We already have the derivative, hey? We know that it's 500 minus a quarter t. So we're going to say where dv over dt is equal to 0. So we're 500 minus a quarter t is equal to 0. And now we're going to solve for t. Okay, now I am running out of space. So let's just talk through this. We're going to move that 500 over. It's going to become minus 500. Then we're going to divide it by negative a quarter. Right, is that fine? We're just solving for t. So when you do that, guys, you're going to get an answer of 2000 hours. All right, so at 2000 hours, that is when the dam reaches its maximum volume, all right, after 2000 hours. And then also that is where it will start to decrease. So you don't have to say like 2000 hours and 1 second or something, okay? Remember, time is continuous, so we can just say 2000 hours for that answer. All right, So guys, these types of questions are a bit, we just rate of change equals derivative. I hope that that will be fine. We're going to practice a few of these and we are going to just do exercise 9.5 on page 234 and let's do numbers 1 to 3. Okay, now guys, just to give you an idea of the next couple of days coming up, we are going to do calculus of motion tomorrow, which has to do with speed, acceleration, displacement, that kind of stuff. It's different from what you do in physics though. We're going to work with derivatives, obviously. Okay, but it's not really that bad. So that will be tomorrow's lesson. Then on Thursday and Friday and Monday, we are going to be revising paper 2 stuff. All right. Thursday, tomorrow is Wednesday, hey, yes. Thursday, Friday, Monday, we're going to be revising paper 2 stuff. On Tuesday, you're going to do your paper 2 test. And then every day after that, we're going to be doing AP. Right. In AP, we are going to be looking at graphs. So we're going to be looking at similar stuff and these kinds of questions. So it is going to seem a bit repetitive. Okay, but we do need to get through it. But guys, we're going to have to push. All right, so every lesson we are going to work, and that is so that I can give you enough time to actually revise your paper 2 stuff. Yes. It depends on when I'm done marking it, but it is going to take me a while. Yeah, we'll see how it goes. But yeah, we do need to push with the AP definitely.